Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.17, crazy file system optimization, supercomputer debugging, and even, I know you love it, a little bit of drama coming up. Let's check the note that Linus left us. In the note, he says that there's no huge surprise for this release, and he also states that he already has a couple of pull requests, even if the merge window for 6.18 isn't even open, which is great. Now, let's get to the featured change. So today, I wanted to highlight two file systems that have had some pretty big change this release. Let's start with BTRFS with experimental support for large data folios. Now, we've seen that last release for ext4, it brought ext4 37% increase in a specific benchmark, which is great. Most likely you'll get around a single-digit percentage increase in performance in your use case, which is very great. But last release, we haven't explained at all what a large folio even is. So let's get to it. Now, to be able to understand large folios, we need to understand folios, and to be able to understand folios, we need the basic TLDR of memory inside of Linux. So let's do it. So inside of your CPU, you've got something that manages memory, and that something will manage it in pages. All of those pages represent 4 kilobytes of memory. Now, your system will do the management of that memory one page at a time. That means that if you have 1 gigabyte of memory, you're going to have a boatload of pages, and that's slow. So the solution that the Linux kernel comes up with is to be able to bundle pages into what it calls folios. So just like in real life, folios are just there to hold your bundle of page. So that way, instead of having to manage all of the page individually, you can address them all using the folio. So that's the TLDR. Now, inside of most file systems, we either have fully implemented folios pretty much everywhere, or we're currently doing the transition towards folios. So when we hear large data folios, that makes kind of no sense, right? Because we expect BTRFS to already be using folios pretty much everywhere. But it's not because we have folios that it means that they are fully implemented, or that they are implemented in an optimized way. You could have a specific part of some system that would have folios, but that would create multiple folios instead of putting all the data into one big folio. Or it could be that it would be more optimal to open up your folio with multiple pages in it instead of using only one page inside of your folio. So all of that optimization work where you check what is best for a specific folio in order to open it correctly, in order to start it correctly, is what a large folio is. So when we're talking about large folios, we're pretty much just talking about making sure that it is implemented to be optimal. Well, now there's more for BTRFS. We have the free space bitmap that is now cached. So inside of BTRFS, you have something called the free space bitmap that shows you where there are some free space and where the space is taken inside of your disk. So now BTRFS will cache this in order to have more performance. So when you create a bunch of small file or a bunch of things in general, it makes things way faster. How much faster? Well, in a specific test that was made for it, we see a 20% performance increase, which is pretty great. We also have better sequential read performance for compressed data. The way that they did it is by implementing a read ahead on that compressed data, meaning that it will read ahead of the data that it needs. So if you ask for more, or if it needs to go further, it will already have it. We also have denser keys on X-arrays for the extent buffer. Now, let's define a bit more with that. So the extent buffer is a buffer that is there to store kind of the structure of the binary tree that is behind BTRFS. So in memory, you have that buffer with where things are on your disk so that you don't have to seek them on your disk. Now, this is in memory inside of an X array. An X array is really just a special array that you can run through, and that really acts as a tree. So you can just run through, and by reading each node, it will transfer you to another node, and at the end, you're going to get to a leaf node, which will give you the result that you're waiting for. Now, the reason why we would want denser keys inside of those X arrays is because if we can have denser keys, they're way faster because they reduce the amount of leaf nodes that we have, so it reduces the amount of things that we gotta go through in order to get our result. Now let's go to our second file system of the day, which is ext4, which got some pretty good change as well. We have, of course, some fixing around the large folios that were implemented last release, so that's great to see. But more important, we've got Baokun Lee. I'm going to start pronouncing a little bit more name. It sounds fun, even if I destroy them. So sorry to anybody that I'm destroying the name of. So Baokun Lee from Huawei, which had an issue. So our unit had some servers with a bunch of containers in it, and he saw that the ext4 code had some weird contention when it came to allocating some blocks. So the allocation code had some limitation and it was slow for some reason that was not really logical. So he went in, rewrote part of the code, and fixed that contention. Not only that, but he took it upon himself to rewrite a little bit of the code so that fragmentation is way more limited. Now, how much of a change? Yes, that's 1468% that you see on your screen. So it does solve a lot of fragmentation and it speeds up a lot of the code. So with that change, you might ask yourself, is ext4 really faster than it was? Well, the answer is yeah. So if we compare 6.15 to 6.17, we see that ext4 is now 18% faster than it was. Now, I'm going to put you on a cliffhanger here, and I'm going to tell you, wait until later in the video, we're going to compare ext4 with all of the other file system. You're going to be surprised. Now let's get into the next feature so that we can get to those benchmark faster. Let's go to the multi-core, which is now unconditional. So before you had the option inside of your kernel to be able to say, hey, I don't want any of the code that handles multi-core system. That would force your system to be single core, and that would also be a little bit more optimal if you only had a single core. Now this is not an option anymore. For pretty obvious reason, most people don't use a single core machine. I don't even know if you can buy any CPUs that are single core today. But in any case, this allows to clear a bunch of unused code for most people that was inside of the scheduling code. So we saw 200 if def and else and that type of conditional inside of the C code that was removed because this is now unconditional. Now, if you're asking, well, what about the single core machine, right? Will they still run? Yes, they will. They will just run with the overhead of having that multi-core system that needs to run on any normal machine, but now it will run also on a single core machine. So no big loss there, but still, it's great for people with multi-core machine, which is most of us. Now let's get into a story that I love a little bit. So let's start and think as if we are filthy rich, okay? We are so rich, we have some AI GPUs, AMD Instinct Accelerator. We're talking about the big guns, okay? We're talking about the 192 gigs of VRAM type of GPU, some heavy hitters. You don't have one, you don't have two, you have 8 of them, okay? Big time 8 GPUs inside of your machine, and your machine has 2 terabyte of RAM. So some big server. Now you're going in, doing AI stuff with your big machine, and you're trying to hibernate it, right? You're trying to put it to sleep because you don't want it to run 24/7, but you don't want to lose whatever you're running on it, right? you're gentle on the on the electricity, right? So you do that and it crashes. This is the real situation of one such kernel devs. Now, let's just explore how Hibernation works on Linux. So Hibernation, at least for the GPU side, the way that it works is it takes the VRAM, drops it into RAM, and then drops it into the swap, into your hard drive. Now, let's just explore a bit more. So if you have 8 GPUs, 192 gigabyte of VRAM, a total of 1.5 terabyte of VRAM, and you have 2 terabyte of RAM, where's the issue? Well, here you're forgetting one crucial part, which is the graphic translation table. The graphic translation table is the part that is inside of your RAM that tells you what is inside of your VRAM and where. So this part can be, at worst, as big as your VRAM. So in that case, you would have 3 terabytes of stuff that you're trying to store inside of a 2 terabyte of RAM machine. So either you crash or you're seeking between your swap and your RAM like a crazy anyway. So what's the solution here? So the devs, what they did is that instead of taking your VRAM and putting it into RAM, they take your VRAM and they put it directly to swap, skipping that step that could cause an issue. Now this wasn't the only issue in that case, because it turns out that it's really slow to go in hibernation and to come out of hibernation. So what's the issue there? Well, it turns out that by default, when you come out of hibernation, when you resume, well, you're taking all of that VRAM and you're uploading it back to the actual VRAM of the GPU. Now that's an issue, because most AI system, or most server of that scale, won't really be re-uploading the exact same thing into VRAM, and most likely, whenever you resume from hibernation, whenever you wake up, you're going to purge whatever is in VRAM anyway. So the new rule that they've put inside of the kernel is, instead of trying to load back all of that memory, it will be on demand. So the GTT, the graphic translation table, will have some place inside of it telling it, hey, if you request that part of memory, you're going to have to go seek inside of the swap instead of, well, searching inside of the VRAM. So this makes things way faster because it will only load if needed. Now let's get into the drama. So of course, when we're talking about drama, let's talk about the king of drama, which is Kent Overstreet, creator of BTRFS. So Kent, this release, tried to do the normal thing that he would do, as in every release that he does, which is send a patch to the merge window. So he sent his changes to the merge window to Linus, saying, and I quote, "So the experimental label is coming off in 6.18. I love the positivity here. Now the big issue is that Linus told us, and him, that he was down on his luck and that he would not work with him again. So that's exactly what Linus did. So Linus ignored the patch that was sent to him, and, well, that's pretty much what's happening now. So of course this ensued a bunch of debate inside of the Linux kernel mailing list. Now, people were yelling at each other, people were trying to have some argument. That part is not really important, it was expected, but where I want to highlight is that we have some very good example that was brought up by none other than Matthew Wilcox, which is a certified kernel unit, which came up with the example of a guy called Palmer. Now, Palmer is the RISC-V maintainer, so he's brought us some good quality code in the last release. Now, there's just one small issue with Palmer, is that he's always late. So every release, since a year pretty much, I've checked for a year at least, has been at the very last day or the day right before of the end of the merge window. Now, that's not optimal because it doesn't give the time to Linus to do his job and review the patch fully. But for some reason, it didn't seem to be a problem for Linus until today. Why was it a problem today, you may ask? Because Linus told us last release that he would be going on a kind of vacation where he wouldn't have as much time within the merge window, so people better put their patch at the start of the merge window or else there would be an issue. So we have a pretty intense chat log, let's say it that way, pretty intense mail from Linus. Let's read it. Let's do a Linus voice here. No, this is garbage, and it came in too late. I asked for early pull requests because I'm traveling, and if you can't follow the rule, at least make the pull requests good. This adds various garbage that isn't RISC-V specific to generic header files, and by garbage, I really mean it. This is stuff that nobody should ever send me, never mind late in a merge window. Like this crazy pointless make U32 from 2U16 helper. That thing makes the world actively a worse place to live. It's useless garbage that makes any user incomprehensible and actively worse than not using that stupid helper. If you write the code out as this code, you know what it does and which is the I word. Maybe you need to add a cast to make sure that B doesn't have a high bit that pollutes the end result, so maybe it's not going to be exactly pretty, but it's not going to be wrong and incomprehensible either. In contrast, if you write make U32 from 2U16, you have not a fucking clue what the word order is. In other words, you just made things worse, and you've added that helper to a generic non-RISC-V file where people are apparently supposed to use it to make other code worse too. So no, things like this need to get bent. It does not go into generic header file, and it damn well does not happen late in a merge window. You're on notice. No more late pull request, and no more garbage outside of the RISC-V 3. Now I would hope there is no garbage inside of the RISC-V parts, but that's your choice. But things in generic header do not get polluted by crazy stuff, and sending a big pull request the day before the merge window closes in hopes that I'm too busy to care is not a winning strategy. So you get to try again in 6.18, early, in that merge window, and without the garbage. So, that was intense. That's not the kind of message that you want to receive from the dear leader, let's say it that way, right? Now, I'm not reading that just to roast on Palmer, because I actually think that he's a good guy, and that he's done a great deal of work in the kernel, and that most of the job that I've seen from him looks good. Now, I'm not a maintainer, I'm not somebody that's qualified to know anything about anything, but for me, the guy's doing his job. So, the part that I want to highlight here is the answer that Palmer gave. So Palmer said, okay, sorry, I've been dropping the ball lately, and it kind of piled up as taking a bunch of stuff late. But that just led to me making mistakes. So I'll stop being late, and hopefully that helps with the quality issue. So what I want to say here is that's the perfect way to answer that kind of message, right? He took the criticism, even if it was pretty darn harsh from Linus, and said, sorry, I'll fix it. Which is exactly what you should do. Now, we can debate hours and hours how rude Linus is and how bad it is. That's your choice. What I'm saying here is that it's not that hard to say that, right? It's not that hard to just say, I fucked up, not doing it again. Thank you. Oh, I haven't said that for Ken, so let's just end the Ken story for here. BTRFS is now externally maintained. So what that means is that the code will be removed from the kernel, and it is recognized by the kernel because it is considered externally maintained. So inside of the maintainer file, we see that Kent Overstreet is there, but no code will be inside of it. So that's a special status that's created for that. Now, to be able to install BTRFS inside of your system, you're going to need to use DKMS. A little bit like you would install the proprietary driver for NVIDIA, you will need to install in the same way BTRFS if you want to use it. Now we're closed for BTRFS. Let's go into CPU change. So let's start with the single run queue proxy execution. Now, what is that? Even before getting into what that is, we need to understand the problem of priority inversion. So we're going to start by thinking about two processes. So let's start with a low priority process. Low priority process is running, and while it's running, it takes a mutex. So a mutex is pretty much a lock that ensures that only one process can do something at a time. So it holds that mutex, and then you have a high priority process that comes online. So that high priority process is running, and it ends up needing the mutex. So normally in that situation, what would happen is your high priority process would shut down, your low priority process would run until it releases the mutex, where it would let the high priority process run. Now, where this might be an issue is if we have the same situation, but while the high priority process is waiting for the mutex back, a medium priority process runs and blocks the low priority process from running. This is standard priority inversion, where a medium priority process or a lower priority process than the one that is currently the highest is running and is taking its place because a mutex is locked by a lower priority process. How do we fix that? Now, the way that they found to fix that through proxy execution is to be able to give the priority to another process, to run a process on the behalf of the higher priority process. Let's make an example. So here, if we have the high priority process, we have the low priority process, and we have the medium priority process, the high priority process could run the low priority process on its behalf at high priority, ensuring that we would unlock the mutex as fast as possible. So this ensures that things go fast and that we don't have that kind of priority inversion. Now you may say, that sounds very simple. Is it really something that we have like right now? Well, the issue is not implementing that part, it's making sure that you don't lock your system permanently because of some crazy setup. So that's why single run queue proxy execution is complicated. It's because they need to make sure that for any situation you don't have one where you've got interlocking things and all of that fun. So now that's solved, and that's behind the kconfig that you can enable inside of your kernel at compile time. Now, if you're wondering where we would see most of that used, because under a standard computer, under your PC, you're probably not having any issue with mutex like that. Now, for a phone, for Android, that would be an issue, right? Because Android will enforce scheduling policies a little bit more strictly, right? Because it needs to make sure that the background process are way more limited to not use too much power, while the foreground process will pretty much always have the power over whatever's going on in the background. So with those harsher policies, it's very important to have something like proxy execution to make sure that things flush through. Let's use that expression. So that's for proxy execution. Now let's go to SMP calls that now are more aware of NUMA topology. Now let's just explain what NUMA is real quick. So when you hear NUMA, you should always think of how far one core is from another. So when you have a NUMA-enabled system, it means that we know how far core 1 is from core 2 and how long it would take for us to execute something on another core. So this allows us to be a little bit more smart about how we're running things in a multi-core system, because then we can choose a core that is more appropriate to run our things instead of just randomly dropping it. And that's a little bit what they did. Now before, you would have a call called SMP call function any that would try to run on first the running CPU, second the CPU around the NUMA core, and if it didn't, it would give up and just run on the first CPU possible. Now this made sense before because, well, before we didn't have that much cores inside of a system. But in a system where we may have multiple different physical CPUs, and inside of those CPUs have multiple subdivision of NUMA, well, that may become an issue, right? We would want to still be as optimal as possible. So now the way that it works with that call is to make sure that they recursively go through every step that NUMA gives you. So it will, in order, try to go through all possible cores, following what is the least costly to the most costly. Now let's go to AMD's hardware feedback interface, the HFI, which has been added to the kernel. Now, when we're thinking about AMD, we're not really thinking about big little architecture, right? So when we're talking about big little, we're talking about a big core, a performance core that is there to do big complicated tasks, and efficiency cores. So that was popularized a lot by Intel, but of course the very smart people that you are know that it has been started by ARM CPUs, but in any case, those kind of CPUs are starting to pop up on the AMD side. So we see the AMD Ryzen AI mobile CPU, I think that they just released it or they're going to release it very soon, is now with that type of architecture. So they have small cores and they have big cores. So it's important for us to be able to know which core is which in order to be able to use them effectively. So HFI, hardware feedback interface, allows us to get that information to the scheduler in order for us to make the best decision possible. That's great. Now let's go to another AMD feature, which is CPU ID faulting support. So let's start with CPU ID. So CPU ID is a CPU instruction that allows you to know what type of CPU you're running on. So you want to know if you have MMX, if you have AVX, you're going to do CPU ID and it's going to pretty much tell you. So CPU ID faulting is the ability to make a fault whenever you run CPU ID on something else than the kernel. So the kernel can know what features you have, but if you have a VM or if you have some kind of user space thing running, you should be able to lie to it, right? You should be able to say to it whatever the hell you want. So the thing that it does is it will fault, and then you can have a tracer that will emulate a CPU ID output in order for you to put whatever output that you want there. So AMD now has that feature. That feature has existed for a long time over in the Blue team since 2017, so great that we now have it on the AMD team. So talking about Blue team, I wanted to highlight how bad things were for Intel, just so that we're not surprised about the fact that we don't get as many patch on the Intel side as usual, and of course in the future. So it's no surprise that Intel is in deep financial trouble, even if there's all that thing going on with the US government and Nvidia. They have released a lot of people. So let's just go through the latest people that went out. So we have Kirill Shutamov that has left Intel after 14 years of work. Worked a lot on TDX. We also have G2 Joseph that has left Intel after 10 years of work. He was the maintainer of the Intel Slim bootloader firmware. Now, this part of the kernel has been orphaned, meaning that there's no maintainer. We have Wu Hao, that now is email doesn't work anymore. Most likely doesn't work there anymore, right? So he was the maintainer for the subsystem related to FPGAs. So 15 years at Intel. Now we have Pravin Pathak that maintained Intel Dynamic Load Balancer. Now Phoronix reported that he still works there, but I think he's gone. I've looked at his LinkedIn and 23 years at Intel and looks pretty gone to me. And Clear Linux, which was the distro that Intel was maintaining, is gone. So despite the fact that benches on Phoronix showed 48% performance increase compared to other distros, which is kind of insane thinking about it, it's gone. So things are not going fine at Intel, and that's really bad for everyone, right? Because for us, we don't get as much patches, we don't get as much improvement, and as we see, it's not because you work at Intel that what you're doing only affect Intel user. Most of the time, you see people that work for Microsoft that will, the person managing VFS, the maintainer of VFS works at Microsoft, right? And you have all of the different part of the kernel that are maintained by those businesses. So it's really bad news, and it's sad. So while we're crying about Intel, let's go shoot on their cadaver, right? Let's go really put them underground because they have some more bad news coming up. So there was a Google engineer named Eric Bigger. Now, I'm talking to the past, but he's still alive, of course, and he tested through FS script if the Quick Assist Technology Accelerator CAT was really that effective. So remember, the Quick Assist Technology Accelerator is a chip that's inside of your CPU that does compression and does encryption for your CPU. So it's supposed to be something that you do asynchronously. So you send that task to that chip and it will return someday with the result. So for big transfers, this should be faster, right? Now that's the question that Eric sought to have some answer. It turns out, not at all. Not at all. The tests were an absolute abject failure where your CPU running under no optimization, we're talking about no AVX 512 optimization, is still faster than using the Quick Assist Technology Accelerator. That's bad. So, of course, most CPU that have those technology has AVX 512, so they're even faster than that. So it's really not good news. Now, just to be clear, it's not only not good news for Intel, but also for Qualcomm, which has their crypto engine, which is exactly the same thing. So those two things were removed from FS script, as we wouldn't want to use them to encrypt anything if they're way the hell slower. Now, this did some very bad thing to other parts of the kernel as well. So when that news came out, Intel's Giovanni Cabadou, he's the maintainer of the Quick Assist Technology Accelerator, so he came out and also lowered the priority of the CAT system inside of the SK cipher and the AEAD algorithms. So pretty much what this means for the general user is that if you have that technology inside of your CPU, you're most likely not going to use it at all because it's just slower. So that it seems that under most circumstances, it's just slower and least efficient. Now let's go into some good news. We have a 3-time performance gain on the CRC32C with AVX 512 processor that have a specific instruction in it. So great news. Now let's go through the GPU change real quick. So we have Intel Z3 Panther Lake OpenGL and Vulkan support that is now enabled and working by default in the kernel. So both the DRM side, so the side inside of the kernel, and the Mesa side, which is the side outside of the kernel, are working. So Panther Lake laptops should be released later this year. So it's great to see that it's already ready. We also see single root I/O virtualization, so SRIOV, for Arc Pro GPU. That is now enabled and working. Now, Arc Pro means that it's only the big non-consumer side GPU that will have such feature. So we're not going to be able to use it if you're a small consumer. But the SRIOV, what it means is the ability for a VM or multiple VM to be able to share a single PCI Express. So using that, you would be able to share different function or, well, share the GPU itself. So this would have been fun, but turns out that most vendors don't allow you to do that on consumer GPUs. Now we also have DRM panic support for a bunch of new things. We have it for Intel i915, and we have it for the Intel Xe kernel driver. So of course DRM panic is the thing that you can send a QR code in front of your screen, yay! And you also have DRM panic for Microsoft Hyper-V driver. I don't know, that doesn't make sense. But anyway, good on them, I guess. And now you also have AMD Smart Mux support. Now, Mux is short for multiplexer. This allows your hybrid laptop GPU, so when you have a discrete GPU inside of your laptop and you have an integrated GPU inside of your laptop, to switch between one output to another. So normally, what you would do if you don't have that multiplexer is that you would have to send the frames through the discrete GPU and then through your integrated GPU in order to get them to the screen. This adds latency, and this also adds some unneeded processing, some unneeded power. Now, the way that they solve that is by literally having a multiplexer, which is just a thing that chooses which path you're going through. So that multiplexer is now enabled. So AMD's technology for those multiplexer is now enabled, which should allow for better latency and better power efficiency. Now let's go into VFS, which now has two new syscalls. So those new two syscalls are called file get attribute and file set attribute. They're there to replace two existing syscalls, which is fsIOC fs get x attribute and fsIOC fs set x attribute. Now, there's two big reasons why we would want to replace those. Number one, the name is absolute garbage, because when you look at it, you're like, oh, maybe it's for extended attributes. And no, it's not made for extended attributes. It was just named before extended attributes were used. So the name is just confusing. And the big issue is that you're most likely going to use this for something a little bit like XFS quota project system. So when you use those quota project system, you can assign, let's say, some quota to a directory. And whenever you create something inside of the directory, you would, of course, have that quota apply recursively to whatever's inside of the directory. Now let's say that you want to remove that quota from a specific file inside of the directory. Now this would work on standard file, but this would fail on special file, because the earlier system call was not able to be applied on special file. So FIFO, sockets, you're screwed. That's not working. Better luck next time. So that was an issue, because if you want to, of course, modify after the fact some quota on some file or some other special attribute, you wouldn't be able to if it was a special file. Now those new syscall, you can apply it to whatever the hell you want, which makes way more sense. Now we also have a new flag for fallocate. So I'm going to say fallocate because it's way funnier that way. So fallocate, the new flag for that syscall is falloc FL write zeros. So falloc is used in order to pre-allocate some files. So if you want to write something and to be sure that you have the place inside of your hard drive, you can use fallocate to punch some hole inside of your hard drive and know that there's some space there for you. Now, the big issue is what if you want that space to be full of zeros? Now, there are some solution inside of fallocate for that. The number one way that you would do that would be to use falloc fl 0 range. That would make whatever space that you're preparing full of 0. But it would not really, because the way that it would do it is it would make sure that in the extent information, it would say this is full of 0, but it would not be actually written down in the data on the drive. So what this meant is that whenever you were to use that drive or to use that file system and to write down on the space that you pre-allocated, you were to need to write those zeros at that time. So that was fairly slow and of course not optimal. Now there's another solution to be able to have a file full of zeros, and you probably know it. It's to use DD. So you can use DD to throw a bunch of zeros inside of your hard drive and make sure that you have a file of a specific size with a bunch of zeros in it. Of course that works, but first, that's very bad for SSDs because you're writing a bunch of data that you maybe don't need to write. And second thing, it's slow because it pretty much abuses your bandwidth. So why would we do that when SSDs have a function inside of them that allows us to just say, this space is full of 0. So this is exactly what this new flag does. So this new flag, what it does is if you have an SSD, it will tell the SSD, hey, from that space to that space, just assume that it's full of zeros, and whenever we will write, you will handle it. So that allows to make things way faster and to not have to completely trash your disk whenever you're trying to write. Now, if your disk does not have that support, if it does not have the unmap write 0 support, it will just throw some zeros at it. But I mean, if you're using that with a very old hard drive, that's your problem. Now, there's also more to VFS. We've got a lot of things that change in the VFS today. So we have the multi-device file system that will better cope with losing a disk. So normally, VFS will shut down the file system whenever it sees that it lost a disk. So that's a little bit counterproductive because maybe you have some kind of RAID 5 with multiple parity where you can make sure to read the data from another disk and you wouldn't want to shut down your RAID because you want to get your data out or something. Now, VFS naturally would not let you do that. So now, instead of launching a shutdown code whenever a disk is removed, it will send another type of code if you use something like BTRFS, which of course support multiple drive, which lets BTRFS or whatever FS you're using answer to the issue. So BTRFS or whatever FS will have the opportunity to answer to whatever crisis is going on inside of your computer. Now, just to be clear, this is called remove bdev. It's a super operation. It's not implemented anywhere yet. So even if you were to try right now with BTRFS on 6.17, it would not do anything. Now let's just go through some quick changes. We have F2FS, which is now under the new mounting API and also has some more folio support, so that's great. And we have HFS, which now has found some maintainers. So that's really great because earlier in the year, we had Christian Browner of Microsoft, which is the maintainer of VFS, which came out on Mastodon and said, hey, buddy, everyone of the kernel, we should probably just remove HFS, right? Because HFS is the old file system from Apple. Nobody was managing it since 2014. So why the hell should we keep that around? That's a fair question, and I completely agree with the sentiment, but some people absolutely want to see it work, which is great, and now it's being maintained and being worked on. Now we also have from BTRFS the ability to compress metadata. So this is something that is, well, not that useful to be honest, but the metadata, which is a very small part of the data inside of your file system, can now be compressed. The big reason why that was is because it's a fairly simple change to do, and it was requested by somebody. Now, BTRFS can be sometimes used as some kind of recovery partition. So if you're using it in that case, compressing everything as small as humanly possible may make some sense, because let's say that you have a phone with a recovery partition containing an image, you don't really care how long it takes for you to recover your phone, right? In those situations, you're probably in way bigger trouble for other reason. So it's great that we have that feature, but it doesn't really change a lot in terms of space, and it's probably something that you shouldn't do unless you're storing something pretty much permanently. Now we also have some read ahead for directories in the readdir function for BTRFS. So here that drastically improved performance. We're talking about a 2.5 times increase. So we have from 900,000 file per second to about 2.3 million file per second. So big change. And the maintainer, Gao Jiang, has stated that he also wants to improve further to try to make it like ext4. So ext4 has some special behavior for slower device where they read ahead in order to try to make things as fast as possible. So there's still some work that would be possible there. Now we've got a weird one from the NTFS 3 driver that now handles symlinks that were created by Windows. Because they couldn't? So yes, it turns out that they couldn't. Also, we can now create symlinks with relative paths. Yeah, things are really crazy in NTFS 3 land. So as promised, let's go to the benchmark. Let's compare ext4 to all of the other file system in Linux. And what we see is, why is ext4 at the top of the list? So yes, ext4, turns out that optimization on the Linux kernel for file system is just a skill issue, okay? Skill issue. So somehow they managed to make up whatever was dragging down ext4 to make it that fast. So great job on everybody that worked with it. We also see that, well, XFS is still doing pretty great, and it's pretty impressive, being that it's a file system that has some more feature to it. But in any case, we can see also that BTRFS is doing well, and if you're wondering why bcachefs is so low, it's mostly because of the block size. So by default, whenever you create a bcachefs partition, it's going to use the 512 block size, which is way smaller than the 4 kilobyte block size that you usually see on other file systems. Why is that the case? Who knows? So you can force the block size, but I think that our friend at Phoronix is trying to not skew anything from a default experience, which absolutely makes sense. Now let's take a look at the benchmark for everything else, for more CPU related things, let's just say it that way. So Phoronix compared 5.15.189, which is a 2021 kernel, compared to this release. And what we see is around a gain of 37% in performance. So we see a healthy gain, we see a good gain, which is good to see. And it's really fun to see that in Linux, going up in version doesn't mean slowing down, which is really appreciated. Now let's just run through a little bit of hardware change. We have Intel that added their IPU7, so IPU is for Image Processing Unit, that should allow some webcam on Lunar Lake and Panther Lake laptop. We also have more support from the error detection and correction code, the EDAC driver, which now covers Granite Rapid D, Wildcat Lake, Raptor Lake HX, and also Bartlett Lake and the Intel Core i5 14600, I don't know how we can say that correctly, and the i7 14700. So we now have ECC for those things. Nice. We also have the Apple System Management Controller that is now supported. So for Apple M1 and M2, we should be able to now reboot them. Wow. Guys, I didn't know that we couldn't reboot a MacBook. Oh my god. Okay, so now we have that, but the SMCD, System Management Controller, is not only handling reboots, it's also handling temperature, voltage, power, all the nice things that we can have data about and that we will need to do, that we will be able to do more with in the near future. Now we also have support for the Raspberry Pi RP1, which is packaged inside of the Raspberry Pi 5. So it's the little I/O controller that is used for camera input, display output, USB 2, USB 3, pretty much everything. So that's great. We also have standardized key code for the performance boost key on some laptop. So it will do something whenever you press it. And now if you want to go into weird mode, we now have support for F13 to F24 keys. Those exist? Yes, they do. So there are some keyboard that actually uses those keys that have this possibility, and somehow, without being mapped, some of those keys still works, which is kind of weird, but in any case, now they are fully mapped inside of the Linux kernel, and they work. Now we also have the support for the MacBook Pro Touch Bar that has been added to the kernel. So I made a mistake back in 6.15 where I said that both M1, M2, and some old x86 had the support for the Touch Bar. That's not true. The support in kernel was only added for M1 and M2, and the preparation code was added for x86. Now x86 gained that full support this release. And while we're talking about Apple, we also have two Apple Magic Keyboard USB-C model, A3118, A3119, that are now in the kernel. Now that was very easy to add because for those two we already had the driver files to make it work. We just needed to add the IDs of those devices in order to make them work. Now, we've talked back in 6.12 about Takeshi Sakamoto. Now, if you remember who that guy is, he's the absolute unit that took up the challenge of maintaining FireWire. Now, he's not only been maintaining it, which would have meant nothing if he didn't write anything, but he actually is writing some code, right? So, since then, he has fully replaced Tasklet with work queues. Now, if you don't know what tasklet are, it's because they're mostly deprecated, and if ever you see them everywhere, it's most likely because you're working with something that is very freaking old. Now, in some comments in 6.9, we saw Linus that said that tasklet were basically deprecated for a while. We've seen talk pretty much ranging 20 years ago about how we should go about removing tasklet. So it's really great that now we have a tasklet-free system. So tasklet are just a way to pretty much answer a software interrupt, which should allow to report some kind of work that you want to do, right? You don't want to do something now, so you use a tasklet to do it a bit later or do it whenever you get that software interrupt. Now, it's important to have FireWire. Why? because macOS has now cut support for it. So the new macOS 26 is FireWire free, and we got it. So we are clearly superior to Apple's system. So now let's get into security, where we have attack vector control that now exists. What is attack vector control? So as more and more vulnerabilities make their way around x86, we should seek a way in order to pretty much fix some specific kind of vulnerability instead of blocking everything. Because sometimes you have some computer that will do only tasks with VMs and may just need to be protected against that specific use case. Or maybe it needs some other kind of protection. But we should have a way to categorize those vulnerability in order to only apply those that make sense for our use case. So this is exactly what attack vector control does. It splits into 5 sets, which is user to kernel, user to user, guest to host, guest to guest, and cross-thread vulnerability. So if you want to pretty much precisely use only the mitigation that should apply to your use case, now you can, using this way simpler method than reading about each of them individually. So now I want you to go back in history, because we're going to see a bug that was put in 1993. So let's start the story with a Linux engineer from Alibaba called Yin Feng Wei. So our friend Ying created an ELF executable from assembly, and it just wouldn't run. Now he was using ARM64 on a 4 kilobyte page size. So his executable did not work. But when he tried using the 64 kilobyte page size, it would run. So he dug up where it would fail, and he found that it was on a specific function. I'll show you on the screen. So it's a load health PHDRS, which is this function. Now, let's just explain a little bit how health executable work. So health executable have what we call the health header, which describes what is inside of the executable. And that health header should contain one or more program header, which shows the different part of the executable. Now, you have that code, the code that you're seeing on the screen, is there in order to check the size of the program headers to make sure that they're not too big. Now, it seems that it wants to compare it to the page size, which is the health min align, and it refuses to execute the binary because of it. Now, what's funny is that health binaries have no such limits, so they're not supposed to be limited by the page size like this. So if the standard for health binaries don't contain this, and we have that check, it should be important to know why that check even exists in the first place, so we don't incur some uncurable damage and the kernel burns down. So we have longtime Linux dev Keys Cook that was sent on a search for the reason why this ever existed. It turns out that it's the version 0.99.15f in 1993 that added that feature, and we don't have any comments or any reason why this exists, so they just removed it, and Linus didn't seem to oppose to it. End of the story. So we don't have any idea why that limitation exists, but there was, since forever, a limitation inside of the kernel which minimized the number of program header that you could run. Maple time, this is maple time. Okay, let's start with the word of the day. The word of the day will be folios, because I like the explanation at the start. Now, I want to explain something to you because I feel like I've lied to you. Last video, I said in 6.16 that I would